Hello again, physics friends. We're back and we're talking about relativistic velocity addition. In a different video, we derive the relativistic velocity addition formula. In this video, we are gaining some intuition for the equation that describes relativistic velocity addition. We're going to use it and practice using it, and we're going to identify three main important features that this equation has. But first, let's remind ourselves of the setup. We have a ball on a train. Alice throws the ball to the right. The train is at rest in the train frame. However, in the ground frame, the train is moving to the right with a velocity vtg, and we're trying to find the velocity of the ball relative to the ground. Okay, so we have these two quantities that we know, and we're trying to find the third. And non-relativistically, what we learned is we just add together vbt and vtg, the ball's velocity relative to the train and the train's velocity relative to the ground, and that tells us the ball's velocity relative to the ground. However, of course, we know that that can't be true at high speeds, because if it were, then that would predict that the ball could travel in excess of the speed of light. And we talked about why time being relative for one observer versus another is the limitation of this expression. Before we write down the relativistic velocity addition formula, I want to identify three features that we hope the relativistic velocity addition formula gets us, okay? So first of all, when we look at low speeds, our relativistic formula better get us back to the non-relativistic formula. In other words, we have some fancy new equation. If we put in small velocities like 10 meters per second or 5 feet per second, we better get back to our common sense expression of the non-relativistic world, right? Because we know that works well at low speeds, okay? Number two, if we have an object moving at a speed less than the speed of light in one frame, then we must not be allowed to make it move larger than the speed of light in any frame or equal to the speed of light in any frame. So if v is less than c in one frame, then we must ensure that v is less than c in all frames. That was the problem with this expression. We could choose a frame of reference in which the ball would appear to go faster than the speed of light, and that's a no-no. On a similar note, if we have an object moving at the speed of light in one frame, then that object must move at the speed of light in all frames. In other words, imagine a photon. If you're in a frame of reference, you see the photon moving at the speed of light. If you change frame of references, we know by postulate 2 of relativity that the speed of that photon is still the speed of light. So if you're moving at the speed of light, then a frame transformation should not change your speed. Okay, those are our three desired features of the relativistic velocity addition formula. Let's write down this formula and then do three examples to show that in fact we achieve these three desired features. Well, here is the equation in all of its glory, the relativistic velocity addition formula. The ball's velocity relative to the ground is given by the sum of the ball's velocity relative to the train and the train's velocity relative to the ground, all divided by 1 plus this quantity, which is the product of those two numerator velocities divided by the speed of light. Well, the first thing to notice is that the numerator here is the non-relativistic velocity addition formula, okay? And so our desired feature number one is basically saying that at low speeds, we need this denominator to equal 1. And you can kind of see that that's going to happen, because if all speeds in the problem are small compared to the speed of light, then we have these two velocities multiplied together divided by the speed of light, but each velocity is much smaller than c, so that ratio is going to be much, much smaller than 1. And when we add that to 1, this denominator is essentially 1, and we recover the non-relativistic velocity addition formula. So we can pretty clearly see that desired feature number 1 is going to happen. The other two may not be so obvious to see, but we will work on them in turn. So we'll do three examples. Each example is going to demonstrate one of these three features, and we'll start by copying down this formula on the next page, which will give us some more space to do our calculations with. Okay, so let's see for example number 1 what happens when we consider only objects moving at low speed. So the ball relative to the train is only a few miles per hour. The train relative to the ground is, say, 20 miles per hour. When you plug in those numbers into this relativistic velocity addition formula, what we find is we get 23.5 point, and I'll just write it out because why not? 999, 1, 2, 3, 4 sets of 9s, followed by 2 9s and a 6 miles per hour. Well, that is awfully close to the non-relativistic expectation of 24, 20 plus 4. In fact, if you'd like, you can write this as 24 miles per hour minus 4 times 10 to the minus 15 miles per hour. So it's so close to 24 that you'd never notice this in your daily life. And so what we see here is at low speed, we indeed recover the non-relativistic limit. Check. And again, the reason for that is that this denominator ends up being 4 miles per hour times 20 miles per hour, which is 80 miles per hour, divided by the square of the speed of light, which is a number that is awfully close to 0. So that when we divide the numerator by 1 plus that quantity, we're basically not touching the numerator at all. Okay, so example 1 passes with flying colors. How about our next example? Okay, so in our second example now, we're going to let the ball move faster, but not in excess or equal to the speed of light, so it goes half the speed of light. We're going to let the train move at also at high speed, 3/4 of the speed of light. And we had talked about this example before, and we showed that the non-relativistic velocity addition formula predicts wrongly or incorrectly that the ball speed relative to the ground is 25% larger than the speed of light. That's not possible. Let's see what the relativistic velocity addition formula says, okay? Well, we know, in fact, the numerator is going to be that 1.25 c, but I'll just write this out fully step by step. So we have half c plus 3/4 c divided by 1 plus half c times 3/4 c divided by c squared. So the c's are going to cancel in the denominator. In the numerator, we have half plus 3/4, that's 5/4 c. And in the denominator, we have 1 plus 3/8, right? 1/2 times 3/4 is 3/8. So that's 5/4 c divided by 11/8. So that's 5/4 times 8/11 c for a grand total of, let's see, 8 divided by 4 is 2, 2 times 5 is 10, 10/11 c. And what's important about this number is that it is less than the speed of light. So 10/11 is bigger than a half. It's bigger than 3/4, right? So the ball does get a boost because of the motion of the train relative to the ground, but it does not get boosted above the speed of light, 10/11 being less than 1. So that's good. We have a velocity less than c, and we transform into another frame, and we find that that velocity remains less than the speed of light. So in our final example, we're basically going to imagine that the ball, instead of being a ball that has mass, is a photon traveling at the speed of light. And our goal is to show that no matter what frame of reference you choose, the ball will always, or the photon will always be measured as traveling at the same speed, the speed of light. So we start with our relativistic velocity addition formula, and we identify in the numerator that VBT is the speed of light. We're not actually going to give a value for VTG, we're just going to leave it as VTG, because what we're going to see is that VTG completely cancels out, which is even more powerful than just picking a specific value. In the denominator, we have 1 plus c times VTG divided by c squared. So one factor of c will cancel in the denominator, but not both. Back up in the numerator, we're going to factor out one factor of c. And now notice that in the numerator, the term in parentheses is the same as the denominator. So that entire term in the numerator cancels the denominator, and we're left with just c by itself. So what this is saying, this is quite a general calculation, that if we have an object like a photon moving at the speed of light, then no matter how fast that platform is moving relative to the ground, an observer on the ground, rather, will tell you that the photon is moving at the speed of light, at 1 foot per nanosecond. So this is showing us that the speed of light is independent of reference frame. In other words, an object that has no mass will always move at the speed of light in every reference frame, independent of the speed of the source or the speed of the observer. Okay, and that's quite generic, quite a generic result. So we see that indeed the relativistic velocity addition formula captures the 3 desired features that we were hoping for, namely that it recovers the non-relativistic limit at low speed. An object that's moving less than the speed of light does not get boosted above the speed of light. To be fair, we showed for a specific example that that was true. We did not show it in general, but it turns out it is true in general. And then we showed in general that an object that has a velocity of c in one frame will continue to have the same velocity in any other frame. And we did show that for all other frames. Okay. I thought we could just close with one final example shown up on the top right. So here we have the example. Alice and Bob in a rocket are moving to the right with speeds half c and 3/5 c respectively. And we're asked in Bob's frame, what is Alice's velocity? So just to be clear, these quantities that are in the picture are the velocity of Alice relative to the ground and the velocity of Bob relative to the ground. And we are asked for the velocity of Alice relative to Bob. Okay, well, we can do this. We don't even need to really memorize the formula. We do the same thing we did for non-relativistic velocity addition. We take those subscripts and we put them as the outer subscripts, and then we put in anything we want in the middle, and that's our numerator. And then our denominator is 1 plus those very same velocities multiplied together, divided by the square of the speed of light. Okay, so we have VAG. We know that that is 1/2 c. We do not have VGB, but we know that VGB is minus VBG, which is minus 3/5 c. So we do have VGB, it's minus 3/5 c. And in the denominator now, we have to do the same thing. VAG is half c, and VGB is minus 3/5 c, and we divide that by c squared. So, as always, these c's cancel in the denominator, and we do some math, okay? So 1/2 c minus 3/5 c, that's our numerator. That's 5/10 minus 6/10 c, or minus 1/10 c. So in our numerator, we have minus 1/10 c. In the denominator, we have 1 minus 3/10. Okay? So we have minus 1/10 c in the numerator, divided by 7/10 in the denominator. The 1/10 cancels, and we are left with VAB given as minus 1/7 c. So what that's saying is that in Bob's frame, Alice appears to be going to the left. Does that make sense? Well, let's look back at the picture. Bob is overtaking Alice. His velocity, his speed rather, is larger than Alice's, and they're going in the same direction. So if Bob is overtaking Alice, in Bob's frame, Alice will appear to be sliding backwards to the left in his frame. And how fast? Well, not half c, not 3/5 c, but rather 1/7 the speed of light. Okay, so this is just a friendly reminder that all of the quantities in this expression are velocities, and you have to be very careful using the right sign and being careful with your indices. And not just in the numerator, but also in the denominator. Okay, good. Well, that's not bad. We've had a little bit of practice now using velocity addition in the relativistic sense. We've shown that it meets these 3 criteria. We've done a sample calculation, and now we're going to do a bunch more practice problems in class and in the book and in the text. Okay, take care, be well, and I'll see you next time.